This video, we're going to talk about Bernoulli differential equations. This is another type of equation that we solve by substitution, and it's going to be written in the form of dy dx plus p of x y equals f of x y to the n. So it looks almost like a linear differential equation with an extra y to the n on the end out here. So we're going to make the substitution w equals y to the 1 minus n. And then when we take the derivative of both sides, dw dx will be 1 minus n, y to the negative n, dy dx. We're going to manipulate our original equation by multiplying by 1 minus n, y to the negative n on both sides to get dw dx and w to show up and turn this into a linear differential equation in terms of w. And you'll see how that works out as we do a few examples here. I'm going to start with number 15 in the textbook. So this is going to be x dy dx plus y equals 1 over y squared. So I'm going to write this as dy dx plus 1 over xy equals 1 over x y to the negative second. So I'm going to I'm going to identify my n as -2. So my w is going to be y to the 1 minus -2, or y to the 1 plus 2 is y to the third. My dw dx is going to be 3y squared dy dx. So I'm going to multiply everything on both sides by 3y squared. 3y squared dy dx plus 3 over x y cubed equals 3 over x. Y squared minus 2 is y to the 0 is 1. So this is dw dx plus 3 over xw is equal to 3 over x. And then this is a linear differential equation. So we're going to take our magic step where we write this as e to the integral of p of x dx as our integrating factor is e to the 3 ln of x is equal to e to the ln of x cubed is equal to x cubed. So we have x cubed times w is equal to x cubed times 3 over x. One of those x's will cancel and give me that x cubed times w is equal to integral of 3x squared dx. So this is x cubed times w is equal to x cubed. This is 3x cubed divided by 3 is x cubed plus c. I'm going to divide everything by x cubed to solve for w. That's 1 plus cx to the negative third. And then we're going to replace w with my y cubed. And I just learned you always solve for y to the n. You know, this y to the power here, that's w, y to the 1 minus n, excuse me. You solve for that and don't worry about solving for y. Some teachers may want you to solve for y explicitly, like take the cube root of both sides. It doesn't make a difference. I just want to avoid getting an answer if this were an even power with a plus or minus a square root in it. So I'll leave it just like that. All right, let's go ahead and look at the next one. Right here. 17 says dy dx is equal to y times xy cubed minus 1. So when we distribute dy dx is equal to xy to the fourth minus y. Let's bring the y over. Dy dx plus y is equal to x y to the fourth. I have n is equal to 4, so w is equal to y to the 1 minus 4. It's y to the negative third. dw dx is a negative 3, y to the negative fourth, dy dx. So I need to multiply by negative 3, y to the negative fourth. Okay. And then I have dw dx minus 3w is equal to a negative 3x. So my mu is equal to e to the integral negative 3 dx. It's going to be e to the negative 3x. So we have e to the negative 3x times w dx is equal to a negative 3x e to the negative 3x. So e to the negative 3x times w is equal to negative 3 integral x e to the negative 3x dx. We're going to need to integrate by parts here with u equals x, dv equals e to the negative 3x dx, and du is equal to dx, and v is equal to a negative 1/3 e to the negative 3x. So we have e to the negative 3x times w is equal to a negative 3 times uv, negative 1/3 x e to the negative 3x minus the integral of v du, like so. So we have e to the negative 3x times w. Negative 3 times a negative 1/3 is a positive 1. X e to the negative 3x. I have a negative 3 times a negative 1 is a positive 3 times a negative 1/3 is a negative 1 integral e to the negative 3x dx. I have e to the negative 3x times w. It's x e to the negative 3x. And I'm going to have plus 1/3 e to the negative 3x plus c. Divide everything by e to the negative 3x, or multiply everything by e to the 3x. W equals x plus 1/3 plus c e to the 3x. And w is equal to y to the negative third, correct? Yes. So y to the negative third is equal to x plus 1/3 plus c e to the 3x. All right, and I will leave that one there. Let's look now at number 19. That is t squared dy dt plus y squared equals ty. Make this dy dt plus 1 over t squared y squared equals 1 over ty. We'll rearrange dy dt minus 1 over ty equals negative 1 over t squared y squared. where n is equal to 2, w is equal to y to the 1 minus 2, w is equal to y to the negative first. So dw dt is equal to a negative y to the negative second, dy dt. We're going to multiply everything by negative y to the negative second. And so we have dw dt plus 1 over t w is equal to 1 over t squared. And so now this is linear in terms of w. This is mu is equal to e to the integral 1 over t dt. So this is going to be e to the ln of t is equal to t for my integrating factor. So d dt of w times t is equal to t times 1 over t squared. So w times t is equal to 1 over t integral dt. So that's w times t is equal to ln of the absolute value of t plus c. And w is equal to 1 over t times ln of the absolute value of t plus c, like that. And w was equal to y to the negative first. This is it wouldn't be that hard to solve for y here by taking the reciprocal. And your book might go ahead and do that. Normally I just solve for w, but in that case, it might be worth it to go all the way to solve for y. Number 21 here. This is going to be an initial value problem. That's a Bernoulli equation. So we're going to make this dy dx minus 2 over x y equals 3 over x squared y to the fourth, where n is equal to 4, w is equal to y to the 1 minus 4 is equal to y to the negative third. Dw dx is a negative 3 y to the negative fourth dy dx. So we're going to make this a negative 3 y to the negative fourth dy dx plus 6 over x y to the negative third equals negative 9 over x squared. Dw dx plus 6 over xw is equal to negative 9 over x squared. Of x, our integrating factor is e to the integral of p of x dx. So that's going to be e to the 6 ln of the absolute value of x, or e to the ln of x to the 6th is equal to x to the 6th. So d dx of w times x to the 6th is equal to negative 9 over x squared times x to the 6th. Cancel 2 of those out, make it x to the 4th. So w times x to the 6th is equal to a negative 9 integral of x to the 4th dx. W times x to the sixth is equal to a negative 9x to the fifth over 5 plus c. And we'll have W is equal to negative 9 over 5x plus c over x to the sixth. I'll write it that way. Normally I write it with negative exponents, but because I have x's and y's coming up here in just a second, W is y to the negative third. So at the point 1, 1/2, we have 1 over 1/2 cubed equals negative 9 over 5 times 1 plus c over 1 to the sixth. So this is going to be 1 over an eighth is going to be 8 equals negative 9/5 plus c over 1 is c. So this is going to be 40 over 5 plus 9 over 5 is c. So that's 49 over 5. And we can come back and write this as 1 over y cubed is equal to a negative 9 over 5x plus 49 over 5x to the sixth. Let's go ahead and just make a common denominator here. Negative 9x to the fifth plus 49 over 5x to the sixth. And maybe make this y to the third is equal to 5x to the sixth over a negative 9x to the fifth plus 49 or a negative 5x to the sixth over 9x to the fifth minus 49. Like that is what y to the third is. That should be a good answer for this. And then I believe that that's everything for this video. So again, these are just two of the important types of solutions by substitutions that we looked at, homogeneous and Bernoulli. There's some other types in your book as well that are less common. And you already know some basic U substitution techniques from Calculus 2 that would fall into this as well, that if you see something kind of ugly in the problem that you want to call U, and it looks like you see something that's the exact derivative of U in the problem, or that you can multiply by a constant on both sides and make du show up, go for it. That type of substitution works very well as well. So look for some additional examples. There's Riccati is another one, and another one begins with a C. I can't remember, Clairant or something like that. But we just don't deal so much with those in this class unless your teacher assigns those to you. Just take a look and see what those substitutions are. They're similar to this process for Bernoulli, where you're going to start off with something complicated and use a substitution that reduces it to something less complicated that's going to be separable or linear or exact or something that you know how to deal with. Again, we only saw all of our homogeneous became separable and all of our Bernoullis became linear. That's very common for those, but you could get some other types of substitutions that you would make where you would get some exact differential equations or something else. So that's it for this video, and I will see you for the next video.